Well, last time I formulated some theorem, Kadayara criterion for a natural morphism to projective space to be a closed embedding, and well, let me recall what are we talking about. So we had a projective variety. With a line bundle on X, and we have a subspace of global sections, maybe the whole space, maybe not a whole, and it gives rise to a rational morphism from X to the projectivization of dual space. So each point goes to the hyperplane of sections vanishing at this point. It's not necessarily a hyperplane. It could be a base point of this linear system. So all the sections could possibly vanish at this point, and then this map is not defined. So it's actually a rational map. Okay, but we give, well, Kadayara gives some conditions when this map is regular and moreover closed embedding. So the first condition is that for any point there is a section that is not vanishing at this point, and then it's regular. Well, maybe let's call it phi. So this implies that phi is regular. Now the second condition is that for any pair of distinct points, there is a section such, well, vanishing at one point, but not vanishing at the other. And finally, the third condition is infinitesimal version of the second condition when the 2 points collide. So the hyperplane L sub x in V of sections vanishing at X well, has the following property that d sigma at X spans the maximal ideal at this, well, the cotangent space at this point, essentially, twisted by our line bundle.
То есть d сигма x это образующее вот это тензорное произведение?
Yes, the differentials, differential this point span the cotangent space twisted by L for sigma in this hyperplane. Okay, so if these three conditions hold true, then phi is a closed embedding into this dual projective space.
Прямое, извините, пожалуйста, а прямое эликс отличается от вот такого фигурного эликс, которое в тензорном произведении стоит? Ну, гиперплоскость.
No, this hyperplane and the L calligraphic is a invertible sheaf line bundle, so they have nothing to do.
Как они связаны между собой?
Well, this hyperplane is the hyperplane in some subspace in global sections of the invertible sheaf. Okay. So let's prove this, and it is very straightforward. So we already know that A guarantees that phi is regular. So we have this morphism phi. It's really a morphism, not a rational morphism, but a regular morphism.
Если бы было сигма x равно нулю, то почему это не было бы морфизмом?
Because this morphism is defined as it sends any point into the hyperplane of sections vanishing at this point. But it could happen that all the sections vanish at some point, and then there's no hyperplane, and you're not, well, it doesn't work at this point. Okay.
Спасибо.
Okay. Okay. So we have this morphism, and well, we so this is some nasty point. So since we know in advance that X is projective, phi is projective, right? Because well, we know that X say goes to X times P star, and this is just the graph embedding, right? But then we know that X is projective, so it's embedded into P capital N times P V star, and then there is a projection to P V star. Okay, so you see it's a closed subvariety of P capital N times the target, so the whole thing is projective. It is the only point where we use this assumption of projectivity a priori known projectivity. Okay, so phi is projective, and now from
I'm sorry,
yes.
I thought that phi is defined as x small goes to the point in projective space, which is
dual projective space, right?
we choose a basis in this V, in this subspace of sections, and we send this small point to S1 of X, 2 points S2 of X, and so on.
Yeah, it's the same in coordinates. Yeah, it's you say the same as I, only in coordinates.
It will be the image will be hyperplane. Yes.
Yes,
in
the hyperplane
V.
sections vanishing at this point. Yeah. Okay. So from our second assumption B, we know that phi is injective. And from the last lemma of last Thursday, phi is finite. Right. So if we know beforehand that our morphism is projective, and know that all the fibers are finite, then the morphism is finite, and in particular affine. It's simultaneously projective and affine. Okay, so that's where we use this lemma proved last Thursday. So now we have to check that it is an isomorphism onto the image. So need that phi
Для чего нам было, что фи конечно? Что из этого следует?
well, you'll see in a moment that phi is a closed embedding. And this means that the structure sheaf O P V star surjects onto, or if you want, the pullback of the structure sheaf surjects onto OX. Okay, so well, that's a local question now. So what we're fighting with, potential problem. So we might have a finite morphism like x equals let's just say the spectrum of k of t, and the morphism is the normalization, so it goes to the spectrum of k of say x squared equals y cubed, something like this. Yes, so that t goes to well, x x is t cube and y is t squared, like this. Yeah, and then this morphism, well, this is further embedded into PV star, but certainly the restriction morphism from the structure sheaf of PV star factors through this nodal curve, and the nodal curve now maps into OX, not surjectively, but rather injectively. Yeah, so well, I don't know how to call it, Y. OY now is embedded into OX. Namely, the image is k of t squared, t cube, and so on. So t is not there, and what we would like to prove that t is there. So we would like to check that it is surjective on the generators of the maximal ideal, but that's exactly condition C.
Я понимаю, что нам нужно доказать только сюрреактивность для того, чтобы понять, что вот эти сечения образуют вложение в проективное пространство, а инъективность нам не нужна.
No, by no means. There is no injectivity. It is just definition of closed embedding. The closed embedding means that at the level of structure sheaf of the structure sheaves, it's a surjection. It's just definition of closed embedding, right? So we need to check that for any point x, the global sections of the structure sheaf modular the pullback of the maximal ideal of the image point is just one dimension.
Почему это эквивалентно сюрреактивности? Откуда это условие берется?
Well, it means that the pullback of the maximal ideal of the image point is just the maximal ideal of point x.
Да, и почему это сюрреактивность тогда получается, что фи сюрреактивна?
Well, the constants go to constants, the maximal ideal goes to maximal ideal, and then you just apply, say, Nakayama lemma.
Спасибо.
But that's exactly what is given to us. So we are given that the pullback of the maximal ideal downstairs spans the quotient like this, and again by Nakayama lemma we are done.
Где было использовано, что φ конечно?
Yeah, it's a good question. Where did we use this? I guess we're using this while applying Nakayama lemma. Yeah, it's true for finite type modules. Yeah.
Спасибо.
Okay, so we are done with this Kadaira criterion. Did I say it was Kadaira criterion? I don't know. I don't have. Okay. So now the most straightforward application of this for curves. Then we already know that any curve C, well, if it's proper, it's projective. So this assumption comes for free, and we have a line bundle invertible sheaf L, and if the global sections of our invertible sheaf necessarily drop if you impose two conditions. So for any divisor d of degree 2, then we have an embedding, closed embedding from C to the projectivization of global sections of this line bundle dual. Okay, so that's just immediate. For 1 point, it will be condition B, and for 2 points, when those 2 points coincide, this will be condition. Sorry, for 1 point, it will be condition A. For 2 points, for two distinct points, it will be condition B. For two coincident points, when C1 equals C2, it will be condition C. Okay, and from this you can say immediately see that for L of high enough degree, it gives you a projective embedding. Okay, and so as a next application to curves, let's speak about elliptic curves. In fact, you already had this home assignment that any elliptic curve is an algebraic group. But let me repeat this from our educated point of view. Maybe it will be somewhat simpler than the solution of your home assignment. So once again, about elliptic curves. So we have a curve E, and we know that its genus is 1. And it immediately implies that the canonical class is trivial. And it also implies that, implies that for an invertible sheaf L of degree D, the dimension of space of global sections is D. I mean, certainly it's true if D is say bigger than 0. Yeah. For example, if D is 0 and you have a trivial line bundle, then it has one-dimensional space of sections, but degree is 0. So there is some discrepancy. If it's non-trivial, then there will be no global sections. Okay, so we know this if you want from Riemann Roch. We can also mention that the dimension of first cohomology is 0 if degree D is positive. Okay, and now the first step is absolutely elementary, and this everybody did in the home assignment. So we consider a map from our curve to the isomorphism classes of line of invertible sheaves of degree 1, and it just sends any point to O of E, the corresponding invertible sheaf, and the claim is this is an well, a bijection. Okay, and this bijection is denoted by Kempf like this, the integral. And maybe let me say one word. Why is it denoted by integral? It makes sense over complex numbers. And in fact, historically, this was the environment where elliptic curves first appeared. And let me say just one word. Why is the integral? So we have this one form. It's a global section of the sheaf of differentials, like this. So it's nowhere vanishing one form, and we view it as a differential one form. Okay, and since it's a differential one form, then we can fix just one point. Let's call it 0, some base point in our elliptic curve. So it looks something like this. There is this base point 0, and there is another point E, a variable point, and we can choose any path going from 0 to E, or maybe some other path. Well, going here and then there and then here, this, and And then we can take really an integral over this path, just of omega, and this would be a complex number. And certainly this depends on our choice of path. And in fact, it depends not quite on gamma, but on its class in the first homology. So given gamma 1 and gamma 2, say their concatenation, gamma 1, gamma 2 inverse, is a loop based at the origin, and it has a class in the first homology of our elliptic curve with coefficients in integers. Okay, and then the difference of those two integrals, so integral over gamma 1 minus integral of gamma 2, really lies in it's a functional on the first homology. Right, is a functional on the first homology. That is an element in the first cohomology, but not necessarily with integral coefficients, right? Because the values of these integrals are not integers. There are some complex numbers. Okay, so
Почему мы рассматриваем гомологии с целыми коэффициентами?
Pardon me?
Почему рассматриваем гомологии с целыми коэффициентами?
Because any loop has that does define a class in the integral homology, right?
Да.
In the integral fundamental, well, in the fundamental group, and hence in the integral homology. In fact, they coincide for the two curves. Okay, so well, we end. So the bottom line is that this integral of our differential form over a path is well defined modulo a lattice, say LE, of so-called period. And by period, maybe I mean some particular paths, some particular loops, like this, and like that. Okay, so the generators of the first homology. Okay. Okay. But in fact, our E is nothing but the quotient of C modulo this lattice of periods. Okay, so it's C modulo some two-dimensional lattice. Okay, and under this identification, this integral is just identity morphic. Okay, any point in E goes to this point of C, the corresponding point of complex numbers defined modulo this lattice of period. And for this reason, this tautological morphism is denoted by integral. Yeah, so far I didn't mention Picard variety. Yeah, somehow in this complex presentation, this integral was a map from E to itself somehow. But then I will also identify it with Picard variety. Okay, but at least the etymology of this notation integral comes from this reason. Okay, so we have to prove this bijectivity, and this is very easy. So.
То есть то, куда мы отображаемся, имеет смысл обратимого пучка степени 1, или какая все-таки идентификация вот этого отображения в себя эллиптической кривой? Какая связь этого отображения с отображением группы Пикара?
Well, I will presently, in a moment, I will prove that this is a bijection, so we can identify our curve with the degree 1 Picard variety. And so we may just identify them. They are the same thing.
Спасибо.
So what do I say? That we know the dimension of global sections of our invertible sheaf having degree 1 is 1. So there is a non-trivial section. So there is a section alpha that is non-zero, but then it must have some divisor. Say D is the zero divisor of this section. And
I'm sorry, do you mean that the dimension is 2? We have this.
No, the dimension is 1.
If it is 1, the sections are only constants, no?
Well, in a sense, yes, but so what? There is a global section.
If you have a non-trivial section alpha, then it is not constant. Then the dimension is.
What do you mean by constant? Our L is
just
not
function which is equal to the same number.
And the sections of L are not functions. They are, so to say, twisted functions, but not functions at all. So you cannot really say that it's constant. There is some regular global section. Okay, we know that it is unique up to multiplication, up to dilation, multiplication by constants. Okay, and that any section has some divisor, and our invertible sheaf is O of this divisor by the very construction. So in particular, this divisor cannot be trivial. It must have degree 1. So it must be just 1 point.
What I say is I meant in my mind then L, if L was a trivial line bundle, then
certainly, yeah, no question. Absolutely, all the sections will be just constants, right?
Okay.
But still, for elliptic curve, if your line bundle is non-trivial but of degree 1, still it will have just a unique section up to dilation. Okay. So that specific property of elliptic curves of genus 1. Yeah, if genus is higher, then it's not true. Fine. So since we know that degree is 1, this divisor must have degree 1, so it must be just 1 point. It's necessarily effective. There are no poles, only zeros. So just 1 point. Fine. So we know that our invertible sheaf must be isomorphic to of just one of this point. And now for different points, we'll have non-isomorphic invertible sheaves. So O E of E1 is never isomorphic to O E of E2 unless they coincide. Since the divisor E1 minus E2 is never principal. Yeah, we proved that if such a divisor happens to be principal, then our curve is necessarily P1, projective line. And we know that our curve is not P1, so there we are. And the bijectivity is proved. And now comes the key point. So we have this global section alpha. It may be viewed as a homomorphism from the structure sheaf to our line bundle, and then we can untwist it. Say alpha prime is a homomorphism from L inverse to the structure sheaf. So we just tensor with L inverse. Okay, and the image of alpha prime is the ideal sheaf for E of negative. Okay, so here is the key lemma. So let us have an abstract variety X. And a line bundle L on the product E times X. And this E times X project to E and to X. Let's call this pi projection to X. And so suppose we know that for any point in X, the restriction of L to the corresponding fiber E times X has degree 1 as before. And then we have a map, say F, from X to the Picard variety. And the Picard variety is identified, say, by integral inverse with our curve E. And we're considering this composition. So the claim is that this composition is a morphism. Okay, and this is a very, very important point of view. So you see, it says that in other words, well, E is the same as pick 1 of E, and is the moduli space of degree 1 invertible sheaves on E. Okay, so so far our pick 1 of E was just a set. Well, it's not just a set; it's an abelian group under tensor. Or well, pick 1 is not an abelian group, but maybe it's a torsor over pick 0. But anyway, it's just a set, and it does not have any algebraic variety structure on it. Yeah. On the other hand, here we formulate some problem. So what is the moduli problem? It is exactly like this. So X goes to the set of isomorphism classes of invertible sheaves on E times X. Okay, this is some functor. So it's a functor from varieties to sets of isomorphism classes. And what is claimed in this lemma is that this functor well, I didn't say that invertible sheaves of degree 1. So this functor is represented by E, which is the same as peak 1. Okay, so given any category, there is a standard way to produce a functor to sets. Yeah, just take any object and take morphisms into this object. Right? Well, it's a contravariant functor, and this is what happens here. But then necessarily from this you acquire the structure of algebraic variety of object of this category of algebraic varieties on the representing object. Okay, so on the one hand, we know set theoretically that this is just peak 1, the set of isomorphism classes. On the other hand, from this lemma, we see that it's a representing object, so it acquires the structure of algebraic variety. So this is a very important lemma, archetypical, and let's prove it.
Could you please repeat the definition of your functor? How was it defined?
Of my functor.
Given a variety, you
yes.
To each point you associate.
To each point, so I associate invertible sheaves on the product. Well, of degree of 1 on each. What should I say this? On each fiber E times X.
So
yeah.
Suppose I give you a variety, and then what do you do with it? So you take each point of this variety and consider a Picard group of the E times this point, or what?
What do I do with it? Well, I just consider all the invertible sheaves on the product E times X with the property that the restriction to each elliptic curve E times X for any point X have degree 1.
Ah, I see. So this is some subset in the
some discrete condition. Yeah.
Okay.
So say topological condition. Okay. So well, now we apply some machinery developed last week, this semi-continuity theorems. So we know that that our invertible sheaf is flat over X, right? Because the local condition, locally, it's just the structure sheaf, and the structure sheaf. I mean, I just say that the projection from E times X to X is flat, and this is clear. Okay, and we also know that the cohomology of all the first cohomology of all the fibers vanish with coefficients in the restricted invertible sheaf. Just because the degree of this line bundle is positive. Yeah, well, we started. We started. Where were we? Where did we start? Yeah, here in the bottom of the second page. Yeah, the first cohomology of positive line bundle on elliptic curve always vanish. Okay, so it means it implies by our big theorems of last week that the push forward under this projection push forward of L is locally free and commutes with base extensions. Okay. In particular, the rank of this locally free sheaf is just the dimension of first cohomology, and we know that the first cohomology, a dimension of zeroth cohomology. The rank of is dimension of zeroth cohomology of elliptic curve with coefficients in Lx, that is 1. So it's an invertible sheaf. And then we have a canonical morphism, say alpha, from the pullback of push forward of L into L. And again, let us twist it by L inverse. So we obtain alpha prime from the pullback push forward of L tensor L inverse to the structure sheaf. Okay, and its image is the ideal sheaf. Well, just let me call it the image of this. So it's an ideal sheaf. Okay, so now since this is an ideal sheaf, it has the corresponding variety of zeros.
Why it is ideal sheaf? We see that it is subsheaf just.
Right, but any subsheaf of the structure sheaf is an ideal sheaf. Yeah, if you give it a moment of reflection, if you recall what is an ideal sheaf, is just a sub sheaf of submodules in the structure sheaf, right? Okay, so this is the zero set. J as a closed subvariety of E times X, and well, I forgot what we were proving. We were proving a lemma. So let's have a sublemma. That this closed subvariety Z is exactly the graph of what we were proving. We want to prove that this set theoretic map from X to E is actually an algebraic morphism of algebraic varieties. Okay, but we're given this set theoretic map F. So first of all, Z consists of pairs E X such that F of X is E. And second, the projection from Z to X is an isomorphism. But then it implies that Z is the graph of an algebraic morphism. Yeah. Okay. So this sublemma proves what we need. It only remains to prove the sublemma itself. Okay, so let's go prove the sublemma. And take a point in our test variety. Then if we take the push forward projection of our line bundle and then its fiber at X, then this is just the global section of E with restriction, with coefficients in restriction of our convertible sheaf to this fiber, and we know that this is just one-dimensional vector space of over our base field, and hence this morphism alpha I defined globally here in the middle of previous page, when restricted to our fiber, is just nothing but the morphism alpha, well, maybe alpha X, I should say, we used in the how to say it, in the lemma about the integral. That is what it is, a bijection. Okay, and it means that when we take this ideal sheaf and restrict it to one fiber, then it's just the structure sheaf of this fiber twisted by the corresponding point E. And this point E has the property that integral of E is just the class of our line bundle restricted to this fiber. Okay, and so the claim that Z is the set of such points is proved. Okay, and we now have to check that the projection from Z to X is an isomorphism. And here we again use the last lemma of Thursday. Because we know that the morphism is projective. Since Z is closed in E times X and E is projective. And hence, we now know that the projection from Z to X is a set theoretic isomorphism. Yeah, right, because over any point of X there was a single point E with this property. So pi from Z to X is finite by the last lemma last Thursday. Okay, but we also know that the fiber of the direct image X is just the global sections of E with coefficients in the skyscraper sheaf. And this is just K. And so the direct image of OZ is OX, and hence the projection is an isomorphism. Okay,
Почему опять нам понадобилась конечность phi?
Because we can conclude only under these circumstances. For example, if we had a projection from P1 to point, then the direct image of structure sheaf of P1 is just one-dimensional vector space. But it does not mean that P1 is isomorphic to a point. It is not. Yeah, so it is only true for affine morphisms. So we need simultaneously projective and affine morphism, that is finite morphism.
То есть это вот в равенстве, где мы рассматривали росток как сечение пучка, вот это вот И? Или вот в каком... вот в этом месте. Понял, спасибо.
Yeah, here, yeah. So we do know that the direct image of OZ is OX, but to deduce from this that OZ is isomorphic to OX, we need the assumption of we need this morphism to be affine. That is finite under these circumstances.
Спасибо.
Okay. Welcome. So we proved the key lemma, and well, on the one hand, this proof may be shorter than your home assignment about elliptic curves. On the other hand, it's very ideologically correct. And also, it's some application of this technique we developed. Okay, and now from this point, we just repeat what you had in home assignment. So let me quickly repeat it, but there will be nothing new. So now to identify E and the Picard of degree 0, the Jacobian, we just fix a point, say 0, the origin in E, but somehow a priori, well, this E will turn out to be a group, and the group is a homogeneous variety over itself. So all the points are sort of the same. And we just pick one, and then it will be the neutral point, the unity of this group structure. But before we choose it, pick it, all the points are well, are the democratic, are the same. And now we obtain the integral somehow shifted, integral 0 from E to, sorry, to the Jacobian, pick 0, namely any point goes to the class of, or maybe, E of E minus 0, like this. So we know that this is a bijection. And now we have to well, as in the home assignment, the pick 0 is a group under tensor product. Okay, so this way E acquires the structure of a group, but we still have to check that this group is algebraic group, so that the operations are algebraic. Okay, so what are the group operations? induced on E via this isomorphism. With the group pick 0. Well, so given 2 points, say E1 plus E2 is E3, such that the line bundle E3 minus 0 is isomorphic to line bundle E1 plus E2 minus twice the origin, and hence E3 is nothing but the inverse integral of the degree 1 line bundle E1 plus E2 minus the origin. Okay, and similarly, how to say it? Say negative E, but in the sense that it's opposite element of the the group E. Is the inverse integral of E of twice times the origin minus E. And here, when I write minus E, means just subtraction in the group of divisors. Okay, so this is a divisor of degree 1. Okay, so these are set theoretic operations, and we have to check the last lemma that E is an algebraic group. So these two operations are morphisms of algebraic groups. Oh, sorry, morphisms of algebraic varieties. And to do this, we will again use this key lemma about representability of functors. So it suffices to construct some invertible sheaves on say the cube and for multiplication for the square for inversion, such that the corresponding morphisms from the key lemma are the multiplication. Well, maybe let me view, say, this as x. Another morphism from E to E, from E times E to E, and the inversion. From E to E. Okay, so then I view the second copy as x. So So on E times E, this line bundle L will be the structure sheaf, or maybe L will be the structure sheaf twisted by the diagonal of first and second plus diagonal of first and third minus the origin times E times E. And if you look at this algebraic well, expression for the sum in the middle of the previous page, that's what you see. Yeah, the expression for E3 is exactly what I wrote in terms of line bundle. Okay, and on E times E, I take L again equals O E squared of twice the origin times E minus diagonal. Again, if I have a look what I want to achieve, it's exactly what I get. And there we are. Okay, so you see that this representability technique is very powerful. It allows to construct algebraic morphisms. Yeah. So since the Picard variety is representing some functor, then morphisms from this representing object to something can be tracked at the level of this functor, and that's what we do. To construct an algebraic morphism, it suffices to construct just an invertible sheaf. Okay.
Причем мы вводили обозначение x для произведения эллиптических кривых.
No, just to make reference to this key lemma.
Понятно, спасибо.
Here we had E times X. And now the role of this X is played either by E squared or by E itself. Okay, extra copies of E.
Понял, спасибо.
Welcome. Okay, so this was well, somehow a heuristic application, and now let's have some other applications, and it will be the Serre criterion of variety being affine. So you probably remember that for an affine variety, any higher cohomology with coefficients in quasi-coherent sheaves all vanish. Okay, and this is sort of converse. So X is affine if and only if for any ideal sheaf J or X, the first cohomology with coefficients in J vanish. Okay, so once again, in one direction, it is some very general theorem we proved via Czech resolution, and in the opposite direction, we will do it now. So you don't need to consider all the quasi-coherent sheaves. It suffices just to consider ideal sheaf. So what do? We first prove that there is an open cover and affine cover. X is the union of D Fi for some functions, global regular functions on X. So first we prove this, and well, we know that our variety is quasi-compact. So if there is any cover at all, it will be necessarily finite. Okay, so it suffices to prove that any point has a neighbor, an open affine neighborhood of this type. Okay. X lies in DF. In other words, it means well, let's start from any or from arbitrary affine neighborhood. Like this, and then we want to find a function, global function, such that the corresponding open subset will be inside U. Okay. So what does it mean? It means that F must vanish on the complement. But it must not vanish at X. That's what we want. So it means that F is a global section of the ideal sheaf of Y.
А для чего нам потребовалось, чтобы f обнулялось в дополнение? Почему оно не может не обнуляться?
Because we want df to be contained in U. So if df is contained in U, it means that f vanishes at the complement.
Спасибо.
Right?
And you here mean that X belongs to DF, X small.
Yes.
Yes.
Yeah, I read this. Okay. So now let's consider the following exact sequence. We have this ideal sheaf of Y. There is projection onto OX, and the kernel is say K, and it is still, so this all lies in OX. So K is also an ideal sheaf. Okay, so we know by our assumption that the first cohomology of X with coefficients in K vanishes, but then it means that a global section 1 in this skyscraper sheaf can be lifted to a global section F in our ideal sheaf, and that's what we wanted. Okay. So once again, we covered what we achieved. We covered our variety X with finitely many affine opens of this sort, dfi for global irregular functions fi. Okay, this was part one. Now part two. We prove that we can find the coefficients a1 and so on, again regular functions on x, such that the sum ai fi is identical one. And indeed, let's consider the homomorphism, say phi from ox to the power capital N to ox, and it takes the collection A to the sum ai fi. Okay, and we know that as a morphism of sheaves, this is surjective. Since X is covered by those affine opens, dfi, and now we want to prove that it's surjective at the level of global sections. We want to lift the identity section to well, to a global section like this. Okay, and again, it is possible, since the first cohomology of the kernel vanish. And why is it true? Just because this kernel, well, if capital N were 1, then this kernel would be a subsheaf of the structure sheaf, that is an ideal sheaf, and we're given this in the condition of our theorem. But now it lies in the direct sum. But then, say we have a flag like this, ox squared, ox cubed, and so on, x to the power n. And each quotient is just the structure sheaf, ox, and we filter our kernel accordingly. Ker 1, ker 2, and so on. For capital N, that's just the kernel of phi, and each quotient, ker I modulo ker I minus 1, lies in ox, and so the first cohomology of ker I modulo ker I minus 1 vanishes, and hence the first cohomology of ker phi also vanishes. Oops, sorry. What did I do? It's 0. Fine. So we're almost done. And we're left just 1 minute. So the third part is that Let say f 1 or maybe sorry, fy 1 and so on, fi whatever di generate global functions on dfi, and so maybe I should say also fi inverse, generate the global functions on this open subset, and let A be the subring in the global functions generated by all these guys. Fij and fi inverse.
ИТ нужно
And also
добавлять?
AI. Pardon me? Pardon me?
Да, я
What
как
was the
раз
question?
про ИТ спросил, но вы уже
Right. Yes, certainly. Yes, thank you. Okay, so we have a morphism psi from X to the spectrum of A, and we know that this is covered by those basic open sets by construction, and also psi is an isomorphism over the fi. Okay, but X is also covered by dfi, and hence psi is an isomorphism. And there we are. That's it.
Извините, а в каком месте доказательства мы воспользуетесь пунктом 2 римский?
Well, this makes sure that the spectrum of A is covered by DFI.
Спасибо.
It was true for X, but it's also true for A, or for the spectrum of A.
Понял, спасибо.
Welcome. So that's it for today. And if there are no other questions, then let me save the draft. And let me stop the recording.